Imagine, if you will, a power so immense it dwarfs the combined output of 1 million nuclear power plants. Now, picture all that energy concentrated into a beam of light. That, my friends, is the incredible reality of the Apollon laser, a groundbreaking scientific instrument nestled in a quiet suburb south of Paris, France. This isn't science fiction. This is cutting-edge science happening right now, pushing the boundaries of what we thought possible. The Apollon laser has recently fired up, claiming the title of the strongest laser on Earth, a beacon of human ingenuity shining brighter than any before it. It's a monumental achievement, a testament to years of dedicated research by brilliant minds. So, what makes Apollon so special? It's all about the petawatts. A watt, as you might know, is a basic unit of power. Think of the wattage of a light bulb. Now imagine scaling that up. A kilowatt is 1,000 watts. A megawatt is 1,000,000. A gigawatt is 1,000,000,000. And a terawatt is 1,000,000,000,000. Apollon operates at an astounding 10 petawatts. That's 10 quadrillion watts, or 10 followed by 15 zeros. This mind-boggling power output, even if only for an infinitesimally short burst, allows scientists to create conditions that are truly out of this world, conditions we've only theorized about until now. To put this into perspective, consider the most powerful lasers in the United States. Recently, scientists at the SLAC National Accelerator Laboratory in California announced a fantastic achievement, a 1 petawatt laser beam. That's an incredible feat, equivalent to those million nuclear power plants, all firing at once for a tiny fraction of a second. Yet, France's Apollon laser operates at 10 times that output. The Zeus laser facility at the University of Michigan also recently achieved 2 petawatts. This isn't just a small step forward. It's a giant leap for laser technology, placing Europe, and specifically France, at the forefront of this electrifying field. Why do scientists crave such extreme lasers? It's because these tools are like superpowered microscopes and cosmic hammers, all rolled into one. They allow us to probe the very fabric of reality, to recreate the conditions found in the hearts of stars or at the birth of the universe itself. With such power, we can accelerate particles to incredible speeds, investigate the mysterious quantum vacuum, which isn't empty at all, and perhaps even discover new laws of physics. The Apollon laser isn't just about being the biggest or the brightest. It's about unlocking the deepest secrets of the cosmos. How does Apollon conjure such extraordinary power, a focused intensity that outshines 1,000,000 suns, albeit for the briefest of moments? The secret lies in delivering an enormous amount of energy in an incredibly short period. We're talking about pulses of light that last for mere femtoseconds. A femtosecond is to a second what a second is to about 31.7 million years. It's an almost unimaginably tiny sliver of time. By concentrating its energy into these ultra-short flashes, Apollon achieves peak power levels that are simply staggering, like focusing the entire energy of a lightning bolt onto a point smaller than a human hair. This remarkable feat is often achieved through a clever technique called chirped pulse amplification, or CPA, a method so revolutionary its inventors were awarded the Nobel Prize in Physics. While the specific proprietary details of Apollon's design are complex, the general principle involves taking an initial weak laser pulse, stretching it out in time to reduce its peak power, making it safe to amplify, then massively amplifying this stretched pulse. After amplification, the pulse is then compressed back down to its original ultra-short duration. This compression squeezes all that amplified energy into that tiny femtosecond window, resulting in the colossal peak power. The intensity generated by Apollon is truly extreme. Intensity in physics refers to the power delivered per unit area, because Apollon can focus its immense power down to a very tiny spot. The intensity at that focal point reaches levels where the laws of physics, as we know them, can be tested in new and exciting ways. The electromagnetic fields generated are so strong they can rip electrons from atoms with ease, creating exotic states of matter known as plasma, and can even begin to interact with the vacuum of space itself. A concept that sounds like science fiction, but is a real area of research. The laser system itself is a marvel of engineering, a sprawling complex of precision optics, powerful amplifiers, and sophisticated control systems. It's not just one laser, but a series of lasers, each one boosting the energy of the pulse before it, culminating in the final awe-inspiring 10 petawatt blast, maintaining the quality and stability of the beam through all these stages of amplification and compression, and then delivering it precisely to a target requires incredible technical skill and cutting-edge technology, all housed within the Apollon facility in Palaiso. With such a phenomenal tool at their disposal, what cosmic mysteries do scientists hope to unravel using the Apollon laser? One of the most exciting prospects is the ability to recreate extreme astrophysical environments right here on Earth. Imagine being able to simulate, on a small scale, the conditions found near a black hole inside a supernova explosion, or even moments after the Big Bang, when the universe was an incredibly hot, dense soup of particles. Apollon's intense energy can generate temperatures and pressures that mimic these cosmic crucibles, allowing us to study matter under conditions previously inaccessible. This opens up entirely new avenues in high-energy physics. Scientists can use Apollon to accelerate particles like electrons and protons to near light speed over very short distances. This could lead to a new generation of compact particle accelerators, much smaller and potentially cheaper than the giant ring-shaped colliders we have today. These super-energetic particles can then be smashed into targets or into each other to study the fundamental forces of nature and search for new, undiscovered particles that could help us understand the universe's underlying structure, perhaps even shedding light on mysteries like dark matter and dark energy. Furthermore, Apollon will be instrumental in investigating the quantum vacuum. According to quantum field theory, empty space is not truly empty. It's a seething cauldron of virtual particles popping in and out of existence. With enough energy concentrated in one spot, as Apollon can provide, it might be possible to boil this vacuum, to rip these virtual particles into reality, creating matter and antimatter seemingly from nothing. This would be a profound demonstration of Einstein's famous equation, E equals mc squared, and could provide deep insights into the nature of reality itself, potentially pushing physics beyond the current standard model. The research possibilities are vast and varied. Scientists plan to use Apollon to study the inner workings of high-density plasmas, which are crucial for fusion energy research. They can investigate the origins of ultra-high energy cosmic rays and mysterious gamma-ray bursts, the most powerful explosions in the universe. There's even potential for simulating aspects of nuclear detonations without conducting actual explosions, contributing to stockpile stewardship and non-proliferation efforts. Each experiment promises to peel back another layer of the universe's complexity, driven by the unparalleled power of this French laser. The development of the Apollon laser is more than just a scientific milestone. It carries significant geopolitical weight. In an era where technological supremacy often translates to global influence, control over petawatt-class laser technology is increasingly viewed as a form of scientific sovereignty. Such capabilities can spur advancements not only in fundamental physics, but also in applied areas like defense systems, next-generation computing, advanced materials science, and even innovative manufacturing techniques. France's achievement with Apollon firmly positions it and Europe as a leader in this highly competitive and strategically important field. This isn't a solitary pursuit, however. The quest for ever more powerful lasers is a global endeavor. Europe's investment in Apollon, coordinated across national and industrial lines with partners like Thales, showcases a strategic vision. Other nations and facilities are also in the race, such as Romania's ELINP, or Extreme Light Infrastructure nuclear physics facility, which is also pushing the boundaries of high-intensity lasers. The friendly competition and collaboration between these international centers drive innovation forward at an accelerated pace, benefiting the entire scientific community and ultimately all of humanity. Of course, building and operating these colossal laser systems comes with immense challenges. They demand groundbreaking innovations in energy storage, thermal management to deal with the incredible heat generated, and robust radiation control to ensure safety. Furthermore, the sheer power involved raises ethical and safety questions that require careful consideration and international cooperation to establish guidelines and best practices. These are not just technical hurdles, but societal ones, reminding us that with great power comes great responsibility to use it wisely for the betterment of humankind. Looking ahead, the future illuminated by lasers like Apollon is incredibly bright. We stand on the cusp of new discoveries that could reshape our understanding of the universe and our place within it. As these powerful beams of light continue to push the frontiers of science, they inspire a sense of wonder and possibility. International collaboration will be key to unlocking the full potential of these magnificent machines, sharing knowledge and resources to tackle the grand challenges of science. The Apollon laser is not just a French triumph. It's a beacon for future exploration, promising a new dawn of discovery for us all